Hello everyone, this is B. Veeramat. Today we are going to discuss the next part of the semiconductor, that is semiconductor diode. See, the next topic is semiconductor diode. A semiconductor diode is a device having the two terminals and typically which allows the flow of current in one direction. That type of device we can call it as semiconductor diode. See, semiconductor diode is basically a PN junction. It is a PN junction. We already learned the concept of PN junction in the last class. See, this is a junction. It is a junction between P-type semiconductor and N-type semiconductor. This is the basic of the diode. So basically, semiconductor diode is the PN junction. Along with the PN junction, which provides a metallic plates at the ends. Metallic plate at the ends to provide external voltage. This is what we can call it as semiconductor diode. Once again, semiconductor diode is basically a PN junction. Along with the PN junction, two metal strips or metal plates are provided at the ends to provide external voltage. See, so to provide external voltage, these metal plates are attached at the ends, either ends of the semiconducting diode, and symbolically it is represented like this. Semiconductor diode symbolically, which is represented like this here, and this a large part. So the arrow which represents P-type of semiconductor like this, and a line here which shows N-type of semiconductor like this, and these two are the terminals, two terminals. Then, so the P-type semiconductor, which is we can call it as anode, and this is we can call it as cathode. One is an anode, other one is cathode, and that arrow, the arrow that represents the flow of current in the forward bias, that shows the direction of flow of current in forward bias. This is about the semiconductor diode, and here this is a junction between the P-type semiconductor and N-type semiconductor. That is what we can call it as PN junction. And here there are negative charged layer, and one is a positive charged layer is present on either side of the P and N type of semiconductor. Because of the positive layer and negative layer, here the potential barrier is created. The potential difference is created, which opposes the diffusion of charges from P to N side and N to P side, which opposes, which is works like a barrier or a wall, which is works like a wall. And this potential barrier, which can alter by applying a voltage, by an external voltage, this potential barrier or potential voltage can be vary or alter. How means that is on the basis of two steps we can explain. One is a PN junction under forward bias, another one is PN junction under reverse bias. The P type of semiconductor is connected to positive terminal of the battery, and the N type semiconductor is connected to negative terminal of the battery. Then that type of we can call that type of connection we can call it as forward bias. Say the PN junction, this is the PN junction, so under the forward bias. the P-type semiconductor, and this is N-type semiconductor, and this is the PN junction. This is the PN junction diode. Here, the P-type semiconductor is connected to positive terminal of the battery, and N-type semiconductor is connected to negative terminal of the battery. Then this is said to be now forward bias. Under the forward bias, what happens here? This the potential barrier voltage. The barrier voltage or potential barrier that can vary by application of this external voltage. Through this external circuit, so we can apply the external voltage. See here, the voltage across this you can call it as potential barrier potential, and this is the applied voltage V. See, once P-type of semiconductor connected to positive terminal and N-type semiconductor connected to negative terminal, if voltage is applied, as voltage increases, see here, as voltage increases, and so these are the poles are here which are positive charged one, and this is the positive potential. Then because of this repulsion force, see here, this is the positive one and these are the positive charges. Because of the like charges, these two are repulsion takes place, and these positively charged holes are attracted towards the negative terminal of the battery. Hence, these holes are passes through the junction and which are moved towards the negative terminal. And here there are some electrons are here, majority charge carriers. These electrons having the negative charges and which are attracted towards the positive terminal, and these electrons are drifting towards or diffusing towards the positive terminal. Then what happens here? There is a decrease in the potential barrier. So the potential barrier starts to decrease. Hence that is represented like this. See here, this is the graphical representation. Initially the potential barrier is this much. There is a maximum potential barrier is there. Because of the potential barrier, these holes and electrons does not process through the junction. But after application of this external voltage, see here, this is an external voltage. Because of external voltage, there is a decrease in the potential barrier. That is VB minus V. There is a decrease in the potential barrier, and this barrier width becomes decreases. The potential wall that is becomes decreases. Once the barrier width decreases, the flow of charges through this is increases. See here, that due to increase in this voltage, external voltage, there are three factors here which affect the three factors. One is there is a decrease in the potential barrier. The width of the potential or potential wall width is decreases. First thing. The second thing is there is a large number of charged particles are flowing through the barrier. Because of there is a decreases in the barrier, that leads to increase the flow of charges through this barrier, and that leads to increase in the current, flow of current through the junction, that is in the order of milliampere. There is a flow of current through the junction, that is in the order of milliampere. There is a maximum current flowing through this. One more here, once the barrier potential equals to applied voltage. See, as applied voltage increases at particular voltage called as a cut-in voltage, at that particular voltage, what happens here? That applied voltage is equals to barrier potential. So once the applied voltage is equal to barrier potential, then so there is, see here, so the opposition is almost equal to 0. There is a very small opposition there, but the maximum charges will flow through the junction. That's why the current flowing through the junction under the forward bias, that is in the order of milliampere. Then, so come to the next point, that is about the reverse bias. See here, PN junction under the reverse bias. The next thing is PN junction under the reverse bias. And here, in the reverse bias, the P type of semiconductor is connected to negative terminal of the battery. See, this is the negative terminal. P type semiconductor is connected to negative terminal of the battery, and N type semiconductor is connected to positive terminal of the battery. Then, once applied voltage, once the external voltage is applied, here these are the holes which are positively charged one and which are attracted towards the negative terminal, and the electrons are the negative charged particles which are attracted towards the positive terminals. Hence, what happens here? So because of this reason, so these charges are moved this side and this move this side. Because of this reason, this potential barrier will increases. The direction of potential barrier and applied voltage both are in the same direction. Hence, the barrier width is increases. As barrier width increases, then that is VB plus V. The voltage becomes here, the already potential barrier is there plus external voltage. Then because of this, the barrier width increases. As barrier width increases, there is no flow of majority charge carriers through this. See, these holes are moved towards this side and electrons move towards this side. There is no flow of electrons and holes through this junction. That's why in the reverse bias, there is no flow of current through the majority charge carriers. There is a small amount of current is flowing through the junction, that is due to minority charge carriers. Here and there somewhat minority charge carriers are available. Those minority charge carriers are passes through the junction in the reverse bias. That's why there is a very small amount of current is there in the reverse bias, that is in the order of microampere. Okay, then one more thing, here the flow of current through the junction which is independent of the external voltage, that is depend on the thermal energy. In the reverse bias, the flow of current through the junction can increase with the increase in the temperature. Nothing but these minority charge carriers are passes through the junction due to thermal energy, not due to external voltage. In forward bias, due to application of external voltage, the charges are moved through the junction and current will increase. But in case of reverse bias, so this flow of charge through the junction is independent of external voltage, which does not depend on this, which is depend on thermal energy. Due to increase in the temperature, then there is an increase in reverse current. This is about the reverse bias, PN junction under the reverse bias. Thank you.